In this video, we'll explore two non-parametric approaches to classification, random forests and bagging. As an example, let's consider building a classification tree of our 9 types of land use using all 147 predictors at our disposal. As a first step, we might end up with this tree. Now, this is obviously too simple. It has only one split and predicts that all images fall into only 2 of our 9 land types. What we know about overly simple trees like this is that they have low variance but high bias. Mainly, if we built more trees using the same algorithm, but different sample datasets, the resulting trees would be stable or similar, but they'd still produce overly simple, hence bad, predictions. In contrast, consider a second tree, which is unpruned or lightly pruned. This tree is overly complicated, so complicated that I've left off the split and node labels because they're so messy. And what we know about overly complicated trees like this is that they have low bias, but high variance. Mainly, if we built more trees using the same algorithm, but different sample datasets, the resulting trees would all be overfit to, hence good at classifying their training data, but they'd be very unstable, hence bad at classifying new data. Let's dream bigger and try to improve upon the tree. Specifically, algorithms exist that maintain the low bias of an unpruned tree while also reducing its variance. The idea is this. Instead of building one unpruned tree, we can build many unpruned trees and then average the results of the trees. But if we're going to build a bunch of trees, it's important for them to be different. There's no point to building the same tree over and over and over. To this end, in order to get different unpruned trees, we can build each tree using different data points. In doing so, though, we have to be a little clever. Because in practice, we only have one sample of data. We don't have endless sets of data at our disposal. However, we can simulate the possession of multiple different data sets by taking different resamples from our one sample dataset. We can then use each resample to build its own tree. Consider an example. There are 675 images of land use in our original sample dataset. To get a resample from these 675 images, we sample 675 images with replacement. With replacement is the key term here. This means that if and when we randomly pick an image from our original sample data, we'll put it back in the pile and maybe pick it again. Consider a small example where we have a small data set with only 4 numbers, 1, 3, 8, and 9. Then 8113 would be a valid resample of the 4 numbers from the sample. Since we basically start back with the original data set after selecting each number here, we sometimes get the same number more than once and other numbers not at all. On average and in general, 2/3 of the original data points will show up in a resample, and 1/3 will be left out. Now, once we have a resample of 675 images, we can build an unpruned tree using this resample. One example is shown here, but remember, we want to repeat this process many times. We want to build many resample trees. Of course, different resamples can and will produce different trees. For example, the 2 resample trees here both use NDVI in the first split, but with different cut points, 0.005 on the left and 0.02 on the right. Again, after repeating the resampling process over and over, we end up with a collection of trees, or a forest. Now, since every tree in a forest can be different, they can also lead to different classifications or predictions. For example, suppose we used each of the 6 trees here to classify the same land use image. Some predict this image is of grass, and others predict that it's of soil. However, the majority of the trees, 4 of 6, predict that this image is of grass. Hence, combining these results and taking the majority vote, it makes sense to classify the image as grass. The ideas that we've intuited here are the shared foundation of the random forest algorithm and the bagging algorithm, which is short for bootstrap aggregating. In general, to classify some categorical response variable y using a set of p predictors x, these algorithms will both take b resamples from the original sample data. Then they'll use each of these resamples to build an unpruned tree. This produces b different trees. The algorithms then use each of the b trees to classify y at a given set of predictor values x. This produces b separate classifications. The forest and bagging algorithms turn these groups of classifications into final classifications by averaging the results of the resample trees. Specifically, they classify y to be whatever was the most common classification among the b trees. Zooming in, let's consider some of the details here. First, when choosing b, the number of resample trees to build, the bigger the better. If we average over a lot of trees, our final model and classifications will be less impacted by unlucky trees that were built by an unlucky resample. And they'll be less variable if we change up the dataset entirely. In practice, b, the number of trees that we build, might be as big as 500 or even 1,000. Second, it's important to build a collection of unpruned trees, since, as we noted earlier, unpruned trees will help us maintain small bias in our model, hence in our classifications. Finally, it turns out that the forest and bagging algorithms take different approaches to building the unpruned resample trees. Whereas bagging considers all p predictors in each split of each tree, hence can end up using any one of these predictors, forests narrow the scope. At each split in each tree, the forest randomly selects and considers only a subset of the predictors. Often this subset consists of either half of the possible predictors, p over 2, or the square root of the number of predictors. To understand the implications, pros, and cons of this choice, let's consider some examples. First, suppose we build a collection of resample trees using the bagging algorithm. What do you notice about these trees? Well, since this algorithm considers all predictors in each split of each tree, the trees end up being pretty similar. Mainly the same variables or predictors tend to dominate the tree. Here, the first splits are all made using the NDVI predictor, and the next splits are either made using some measure of mean G, brightness, or mean R. What's more than the resample trees being similar to each other, they're all similar to the tree that we'd get if just using all of the sample data, shown here in the red box. Since our bagging trees are so dependent upon this sample data, our bagging results might change quite a bit if we changed up the sample data. That is, if we used a different set of sample data. As such, though our bagging results tend to be less variable, hence more stable than the results of a single tree, we can do better. This is where random forests come in. Recall that this algorithm only considers a randomly selected set of predictors in each split of each tree. As such, the resample trees can end up being pretty different from one another. That is, they've been decorrelated. For example, the resample trees here use different predictors in each of the first few splits. What's more than the resample trees being different from each other, they're different from the tree that we'd get if just using all sample data, shown here in the red box. That is, they're less directly dependent upon the sample data that we happened to start with. As such, our forest results won't change as much as the bagging results if we happen to switch up our sample data. That is, forests are less variable, hence more stable, than bagging and trees. Stepping back, let's summarize some comparisons of bagging and forests versus trees. Bagging and forests share two major drawbacks. Since they both require building many trees, they're more computationally expensive than building a single tree. Second, we can't really plot the many trees combined by the bagging and forest algorithms. Or we could, but it wouldn't be very useful. As such, these algorithms aren't as readily interpretable as the tree algorithm. However, the pros tend to outweigh the cons here in terms of performance. By combining information from many unpruned trees, bagging and forests tend to maintain the low bias of unpruned trees while also reducing variance. That is, these methods will be more stable and are less prone to overfitting. Relative to each other, forests have some advantages over bagging. Not only do they further reduce variance by decorrelating the trees, they're more computationally efficient. They only have to consider and compare a smaller subset of the predictors in each split, not all of them. Finally, forests and bagging are just two of many ensemble methods. The word ensemble might make you think of music. A musical ensemble combines the outputs of multiple instruments. Similarly, a machine learning ensemble method combines the outputs of multiple machine learning algorithms. By this definition, bagging and forests are ensemble methods. They both combine the outputs of multiple tree algorithms. And in general, ensemble methods enjoy the same benefits as bagging and forests. They decrease algorithmic variability from sample to sample, hence provide more stable classifications than might be obtained by any algorithm alone.